Hey you guys, welcome back to another video. Today we're going to be covering topic 1.5 polynomial functions and complex zeros. Given a polynomial function p of x, if p of a equals 0, then a is a 0 or a root of p of x. Just as a reminder, the word zeros is basically just referring to your x-intercepts. So you need to be familiar with all of the words: zeros, roots, x-intercepts. Solutions is also one of them. So if they ever ask you what is the zero of the function, you need to know that they're asking you for the x-intercept. When we think of x-intercepts, we know that that is the point where the graph intersects the x-axis, and at any point that you're touching the x-axis, your y value always has to be 0. So for any 0, which is also your x-intercept, we know that the y value has to be 0. And we also know that another way to say y is f of x. So f of x will be 0. So if they give you a function, let's say f of x equals x minus 3 times x plus 2, you would replace that f of x with 0 and then solve for the x values, and that will give you your zeros. Okay? The next sentence says, if a is a real number, then if x equals a is a 0 of p, then x minus a is a linear factor of p. So let me give you an example here. Let's say, for example, we get f of x equals x minus 3 times x plus 2. Okay, and I say, what are the zeros? What you're going to do is replace the f of x with 0 and set it equal to the function. Now, when your equation is already in factored form, what you can do is separate the factors and set them each individually equal to 0. If they are not in factored form, you will have to factor them by yourself. And then after that, you can solve for x. So here you would add 3, so x equals 3, and on the other one, x equals negative 2. So what we have here are the zeros of the function, and where they came from, which was these up here, those are what is called your linear factors. Okay, so that's what the second sentence is saying. So if x equals a is a 0, then x minus a is a linear factor. So here we had x equals 3, and the linear factor was x minus 3. So that's all that's saying. It kind of sounds a little bit more confusing than it actually is. Okay, so repeated zeros, that's when you have multiplicity. So if a linear factor x minus a is repeated n times, the corresponding 0 of the polynomial has a multiplicity n. So for example, back to this problem that I gave you earlier. Now remember, if a variable does not have any exponent, then that exponent is an imaginary 1. So this factor didn't have an exponent, so we can say there's an imaginary 1 on both of them. That exponent is the exact number of the multiplicity of each factor. So since x equals 3 came from the linear factor x minus 3, which had an exponent of 1, then it would have a multiplicity of 1. And then the same thing for x equals negative 2, it would have a multiplicity of 1. Okay, if this one had a multiplicity of degree of 4, then this one would have a multiplicity of 4. If this had a degree of 7, this would have a degree of 7. So whatever linear factor your 0 came from, that exponent, that degree, is the multiplicity of your 0. Okay? Typically, we know that the graph of a polynomial passes through the zeros on the graph. However, when a 0 has a multiplicity that is greater than 1, the graph will behave differently near the 0. The function y equals negative 0.01 times x plus 4 times x plus 1 cubed times x minus 3 squared is graphed to the right. Okay, what we're going to do before we look at the graph is find out the zeros by hand. So remember, we know that for every 0, the y has to be equal to 0. So I'm going to replace this y with 0, and I'm going to solve it over here off to the side. Okay, so we had 0 is equal to negative 0.01 times x plus 4 times x plus 1 cubed times x minus 3 squared. Okay, now thankfully it's already in factor form, so that saves us a step. When it's in factor form, you can separate every single factor and set it equal to 0. This negative 0.01 by itself is also a factor, so you can separate that. Negative 0.1 equals 0, x plus 4 equals 0, etc. Okay. Now, when you think about the statement negative 0.01 equals 0, we know that's not true. There is no way that any number is going to equal 0. If I put negative 5 here, negative 5 does not equal 0. Negative 10 does not equal 0. Negative 100 does not equal 0. So if you ever have a single constant number with no variable, meaning there is no x on it, you can just disregard that because it's not going to equal 0. Okay. On the next one, we know we have x equals negative 4. And if I look back at the factor, x plus 4 didn't have an exponent, so that degree has to be 1, which means that my multiplicity down here will also be 1. Okay. On the next one, we do have to get rid of the cube before we subtract the 1, so you're going to do a cube root. And what you do to one side, you do to the other side. Now, anytime you want to get rid of an exponent, you're going to do that number root on both sides. So you should be familiar by now with the square root and the cube root. You could also do the 4th root, 5th root, 6th root, 7th root, 8th root, 1000th root, 2000th root, 1,000,000th root. If you have any number here, if I have the 73rd power over here, I can do the 73rd root, and these will always cancel out. It even works with fractions. If I had 1/3 power, I can do the 1/3 root, and they would cancel out. Okay, so you can do any root that you want to get rid of any exponent that you may have that's in your way. And then so now the cube root and the power of 3 cancel, and you're left with x plus 1. The cube root of 0 is 0. Subtract the 1, you get x equals negative 1. Okay, now if I look back up at the top, that degree was 3, so this 0 is going to have a multiplicity of 3. Okay, now on to the next one, we got to get rid of the exponent of 2, so I'm going to square root on both sides. The square and the square root cancel, we get x minus 3. The square root of 0 is 0, add the 3, you get a positive 3, and this factor had a degree of 2, so the multiplicity would be 2. Okay. So those are our 3 solutions. Now, these are actually the exact solutions that we see on the graph below us right here. So we have that x equals negative 4, x equals negative 1, and x equals positive 3. Okay, for the solution that we had got at x equals negative 4, we said that one had a multiplicity of 1. Okay, the multiplicity of 1 is like the basic x-intercept you have seen for a few years. All it's going to do is cross the x-axis. Nothing else, it's not that special, it just crosses the x-axis. Now, at x equals negative 1, we said there was a multiplicity of 3. I see that this one also crosses the x-axis, but this one does look a little bit different than multiplicity 1 because multiplicity 1 was just a straight line, and I see this one is a little curvy. So why is that the case? The reason why, I don't know if you remember this from the last lesson when we learned about points of inflection. Remember that points of inflection is a point where your graph changes concavity. So you see that this part here would be concave up because I see that smiley face, and then it changes to concave down. Right now I see a frowny face. So anything that has multiplicity 3 will also be a point of inflection. Okay, so they cross the x-axis, and in addition to that, they're a point of inflection. At x equals 3, we said that that 0 had a multiplicity of 2. Okay, this one does not cross the x-axis. This one basically just bounces off. So it approaches the x-axis, and then it goes back to where it came from. So notice it could be like this. It could also happen like this if it went above. So it doesn't have to be strictly below. As long as it does not cross the x-axis, it touches it and then goes back around, it could have a multiplicity of 2. Okay, so the multiplicity of a 0 is the degree of its factor. So we can include the multiplicity when we list the zeros. So we had said that x equals negative 4, and that one only had a multiplicity of 1, so you don't really have to say a multiplicity of 1, but you can. X equals negative 1 had a multiplicity of 3, and x equals 3 had a multiplicity of 2. At x equals 3, the multiplicity is 2. The graph of the polynomial is tangent to the x-axis, meaning that the graph bounces off the x-axis. The graph of a polynomial will always be tangent to the x-axis at any 0 with an even multiplicity. Okay, so I want you to underline or highlight this part. So the part that the graph bounces off the x-axis occurs at any 0 that has an even multiplicity. Okay, so these two go hand in hand. So earlier we just talked about multiplicity 2. We can have multiplicity 4, 6, 8, etc., etc. So if I changed this one to have, instead of this 2, let's say I had 200. That's still an even number. This 0 would still behave the same way on the graph, that it would bounce off the x-axis, okay? So it doesn't matter how big the number is, as long as it is an even number, it'll still behave the same way. It'll be bouncing off the x-axis, okay? Now for odd multiplicity, and this is going to exclude 1, so except 1, you're going to cross the x-axis and you're going to change concavity, meaning that that odd multiplicity will always result in a point of inflection, okay? So you can have degree of 3, 5, 7, 9, etc. Okay, so just as an example, let's say, again, remember this function was this graph. Okay, so let's say x plus 4 is always a power of 1. Let's say I have a crazy number like 173 over here, and then let's say I have another crazy number like 224. Okay, so those are crazy big exponents, but because that second factor is still odd and the last factor is still even, it'll still produce this same graph where this one has a point of inflection, this one bounces off, and this one goes straight through. So multiplicity 1 just crosses like a normal x-axis, x-intercept, and then every odd multiplicity will cross the x-axis and it will change concavity, and every even multiplicity will bounce off the x-axis. Okay, so let's do some examples here. For each of the following polynomials, determine the degree of the polynomial, find all the real zeros, and state the multiplicity for each 0. Okay, so what we're going to do is set f of x equal to 0. So that's the first step every time they ask you to find the zeros. Okay, now I see that this is already in factor form, which makes this process a lot easier. So we're going to separate every single factor and set it equal to 0, and then we're going to solve them separately. Okay, now when you're solving for variables, I'm going to make a note somewhere over here. So when you're solving for a variable, you're going to do PEMDAS backwards. So when you're simplifying, you do it forwards, but when you're going to be solving for something, you're going to do it backwards. So first, you're going to ask yourself, is there anything I can add or subtract? If there isn't anything, you're going to move on. Is there anything I can multiply or divide? Then you're going to see if there's any exponents you need to get rid of. And then finally, you're going to tackle anything that's inside of the parentheses, okay? So if I look at the negative 2x cubed, there is nothing I can add or subtract. But there is something I can multiply or divide, specifically that negative 2. I can divide it out because it was being multiplied. To undo multiplication, I do division, right? Negative 2 and negative 2 cancel out. And then you're left with x cubed, and 0 divided by negative 2 is 0. Okay, now just as a side note, I just want to reiterate, negative 2 divided by negative 2. Any number divided by itself always equals 1. So I just want to, reinforce that things don't just disappear or cancel out, or they don't equal 0. Any number divided by itself is 1. So in reality, we're left with a 1x cubed, 1 times x cubed. But because it's just 1, we don't write it. I just wanted to point that out in case your other teachers have never mentioned that before. Okay, now we're left with x cubed. Before we get to x, we're going to have to do the cube root on both sides so that the cube root and the cube cancel out. And then we're left with x equals 0. I kind of run out of space here. X equals 0, and this has a multiplicity of 3. So if you look back at the factor, the one we were solving had a degree of 3, so that means my multiplicity from that factor has to match. Now let's move on to the next one. X equals negative 1. And I see that this one didn't have a degree, so there is an imaginary 1 there, so that means the multiplicity of this one will also be 1. Okay, on to the next one. So remember, you're doing PEMDAS backwards. Before you can do anything inside the parentheses, you need to get rid of the exponent. So we're going to square root both sides. The square root and the square cancel. You get x minus 4 equals 0. So x is equal to positive 4 with a multiplicity of 2. Because if you look at that degree, the degree was 2 from that factor. Okay, so now what you're going to do to find the degree number, is that you're going to add up all the multiplicities. Okay, so for this solution, my degree would be, I had 3 plus 1 plus 2. That equals to 6. Okay, so my degree is 6. And then to write out my final answer, I'm going to say I had a 0 at x equals 0 with multiplicity 3, x equals negative 1 with multiplicity of 1, and x equals 4 with a multiplicity of 2. And that would be our final solution. And then always make sure that all of your zeros add up to your degree. So again, 3 plus 1 is 4, and 4 plus 2 is 6. So that's how you can double check that you counted right. Okay, let's go on to the next problem. Here we have g of x equals 3 times x squared minus 4 times x minus 2 to the power of 4. Okay, so if necessary, you can factor. On this one, you can do either or. You can factor that x squared minus 4, or you can solve it as is. I'll do both just in case, and then you can pick whichever you prefer. Okay, so first step is set it equal to 0, and you get 3 times x squared minus 4 times x minus 2 to the power of 4. Separate everything, set it equal to 0. And on this one, I'm going to put or. So I'm going to solve it in 2 different ways so that you can pick which way you want. And then this one, I'm going to solve it over here, x minus 2 to the power of 4. Okay, now remember, when you have a single number that's equal to 0, we're going to disregard that it does not equal 0. 3 never equals 0. Okay, so here's going to be 2 different ways that we can solve this. The first way is going to be to do difference of perfect squares. So I can rewrite x squared minus 4 as x plus 2 times x minus 2 equals 0. So if you're proficient with difference of perfect squares, you should recognize that you can take the square root of x squared and the square root of 4, and that's how you get those 2 factors, right? Because the square root of x would be just 1x, and then the square root of 4 is plus or minus 2. So then from here, you would then do the process again where you separate the factors and set them equal to 0, and then you get x equals negative 2 and x equals positive 2. And then from these factors, I had a degree of 1, so that means that each of these would have a multiplicity of 1. Okay, so that's one way. Now I'm going to do the other way. Okay, another way you can do it is to add 4. So now you have x squared is equal to 4. Now you have a square that you need to get rid of by doing the square root, and the square and the square root cancel, and you're left with x equals the square root of 4. Now, it is very important that you don't forget this. Any single time that you take the square root of a number, you always need to do plus or minus, okay? And then the square root of 4 is 2. And then from here, you get the same answers that we had before, which is x is a positive 2, and then x is equal to negative 2, okay? And then those also have a multiplicity of 1. Because from the original factor that this came from, we had left it like this as a factor by itself, and this one had a little degree of 1 on the back, so these would have a multiplicity of 1, just like the first method that I did. Okay, so you might be asking why the plus or minus. Okay, so this is just as a side note, you don't need to write this down. We had, before we had the solution, our previous work said x squared equals 4. If you forget the plus or minus and all you say is 2, you are half correct. 2 squared does equal 4. But so does negative 2 squared. Negative 2 squared also equals 4. So if you forget to do plus or minus, you will be missing half of your answer. Okay? And then so here we have the last factor. Set it equal to 0. To get rid of the power of 4, I'm going to do the fourth root, so that the fourth root and the power of 4 cancel, and I'm left with x minus 2 equals 0, then x equals 2, and this one would have a multiplicity of 4. Okay, so now to write the final answer, for my degree, I'm going to count up all of the multiplicities. Okay, so remember, these are the same answers. I'm only going to count them one time. 1, 2, 3, 4, 5, 6. Okay, so my degree is 6. And then let's see the answers that we got. I got from one side x equals 2 with a multiplicity of 1. The other one I got x equals negative 2 with a multiplicity of 1. Oh, but then on the other factor, I also got x equals positive 2 with a multiplicity of 4. So when that happens, so notice I'm going to circle it. This one and that one are the same exact 0. They're both positive 2. When that happens, you need to add the number of multiplicities. So in reality, when I had written multiplicity of 1 here, that would be incorrect. I would still need to go back and make sure to add them. So 1 plus 4 is 5. So the degree the multiplicity of x equals 2 is actually 5. And then again, 5 plus 1 would be your degree, which is 6. Okay, let's go on to the next one. For letter C, again, start by setting your y equal to 0. You get x cubed minus x squared minus 6x times x squared minus 7x plus 12. Okay, first thing you're going to do is separate your factors. Set them each equal to 0. Okay, now if you're not that proficient at factoring, I do have a factoring video on my YouTube channel. I would recommend that you watch it. It's about 17 minutes long. But if you're proficient with factoring, then that's good. You will need factoring for a lot of the stuff coming up in the future, especially the second half of Unit 1 and the second half of this lesson. So if you are not good at factoring, you forgot how to factor, I would just watch that video, refresh your memory. I know that you know how to do it, you probably just forgot and need a refresher. Okay, on this one, I do see that all of them have a common factor, so I'm going to use the factoring method, which is called greatest common factor. They all share one x in common, so I can take an x out. If I take an x out of x cubed, I would be left with x squared. If I take an x out of negative x squared, I would be left with negative x. And if I take an x out of negative 6x, I would be left with negative 6. Okay, so now I have this random x in the front. I can keep factoring. Now I can use x method. So I'm going to bring this down here. I have that x in the front. And from this quadratic, I'm going to get two linear factors. Okay, so you're trying to come up with two numbers that multiply to negative 6 and add up to negative 1. So don't forget there's an imaginary little negative 1 here. So your linear factors, if your a equals 1, your linear factors will just be x plus or minus a number. Okay, so I'm trying to get two numbers that multiply to negative 6 and add to negative 1. Those two numbers would be negative 3 and positive 2. Okay, now I have all of these numbers. I would separate all of these again, set them all equal to 0. That's a lot of work and I'm running out of space. So I'm just going to write the answer. So x equals 0, x equals 3, and x equals negative 2. Okay, now all of these factors had a degree of 1, 1, and 1. So all of these are going to have multiplicity 1. Okay, now let's look at the other one. So again, we have 1 in the front. So we know that we're going to get two linear factors that start with x. It's different when your leading coefficient is not 1. Okay, so it's a similar process, but it's more steps. So again, if you forgot how to do that, just go look at the video on my YouTube channel called Factoring Review. Okay, so two numbers that multiply to 12 and add up to negative 7, that would be negative 4 and negative 3. You separate them, set them each equal to 0. You're going to get x equals positive 4 and x equals positive 3. And again, these linear factors had a degree of 1. So that means that these zeros will also have a multiplicity of 1. Okay? All right, last step is to count up all the multiplicities so that you can get your degree. So I have 1, 2, 3, 4, 5. So my degree would be 5. Okay? Now let's find the zeros. Okay, we had one solution which was x equals 0. I don't see any other zeros here, so I know that one is going to be what we had before, which is multiplicity 1. X equals 3 is another one, but I do see another x equals 3 over here, so I know that I'm going to need to add these together. So x equals 3 will have a multiplicity of 2. And then the final two were different. X equals negative 2 had a multiplicity of 1, and x equals 4 had a multiplicity of 1. Okay, So I'm going to box in this final solution and always count up to make sure you did it right. 2 plus 1 is 3, 4, 5. Okay, so that is zeros and multiplicities. Okay, let's move on a little bit. We're going to start talking about complex roots. Some polynomials have roots that contain an imaginary number. This means that you will not see them on the graph. The graph of f of x equals x squared plus 1 is shown on the right. Okay, so they gave us f of x equals x squared plus 1. So let's do the same process we did earlier, which is to set f of x equal to 0, and then you can solve. Now, you might be thinking, oh, I can do the difference of perfect squares because it was similar to the other one you did, but in reality, you can't. If you ever have a plus, you cannot do difference of perfect squares. The word difference literally means to subtract. Okay, so when you're finding the difference, you are subtracting. So if you don't have a minus here, you cannot do the difference of perfect squares. So here what we would do is subtract the 1 on both sides. You get negative 1 equals x squared. And then you would take the square root. Okay, the square root and the square cancel, and we would be left with x equals plus or minus. Remember, anytime you take the square root of a number, you need to do plus or minus. Now, you cannot actually take the square root of negative 1. This is actually equal to the imaginary letter I. Okay, so I'm going to put over here that the square root of negative 1 is equal to plus or minus the letter I, and that's never going to change. You cannot take the square root of a negative number. So this is actually two solutions. Remember, let me write it sideways instead. I'm going to write it this way. So we have 1, 0 that x is positive I, and 1, 0 where x is equal to negative I. Okay, and then these are each going to have a multiplicity of 1. Okay, let me give you another example in case you're still confused about the I. Okay, if I tell you to find the square root of negative 25, you can still take the square root of 25, which would be plus or minus 5, but because you have that negative in it, you would need to add that I to the back. So the square root of negative 25 could be plus or minus 5i, but it would be incorrect to not put the I and just, do plus or minus 5. Okay, now a few lessons ago, we talked about how to find the leading term and the leading coefficient and the degree of that leading term. So from x squared plus 1, remember that whatever term has the highest exponent here, it would be the x squared, and that degree would be your the degree of the thing. So that means that this one has a degree of 2, and we have two zeros back here, x equals I, x equals negative I, and they each have a multiplicity of 1. Remember, if you add up the multiplicities, they equal the degree. Okay, so basically you see that on this graph, this is the graph of x squared plus 1. You have 0 real roots. Never does this graph touch the x-axis. So there are 0 real x-intercepts, okay? But there are 2 imaginary roots, 2 non-real roots. So I can put that on here. There are 2 non-real zeros, okay? All right, moving on. All imaginary roots come in pairs. So if a plus bi is a root of f of x, then so is a minus bi. Okay, these are called conjugate pairs. That's a new vocabulary word. You can underline or highlight that. Okay, when you're finding the conjugate pairs, I'm going to make a note here. The sign of a does not change. You will only change the sign of the term with the letter I. Okay, so notice that here I had a positive a, and for the conjugate pair I still have a positive a. If this had been a negative a, then this would also be a negative a. You do not change the sign of the first part. What you will do is change the sign of the part of the term that has the letter I. So we went from a positive bi to a negative bi. Okay, now you will not always have this a in the front. If a is missing, the only number that you can add or subtract that's not going to make a difference would be 0. So if you do 0 minus bi, that would just be negative bi. Same thing here, if you do 0 plus bi, it would just be positive bi. So you will not always see the letter A if the letter A is equal to 0. Yeah, that's it. So all you would do is change the sign of the part that has I. Okay, let's try some examples. We're going to be finding the conjugate pair of the following complex numbers. So for letter A, all we have is 4i. That means that A is not there. So all I'm going to do is change the sign of the part with I. So the conjugate pair would be negative 4i. The conjugate pair of negative I would be positive I. The conjugate pair of 2 minus 3i, remember you don't change the sign of A, but you do change the sign of the term with I, so I would put 2 plus 3i. And then the last one, don't change the sign of A, change the sign of the part with I, so negative 4 minus 2i. So finding finding conjugate pairs is not that bad. Okay, the fundamental theorem of algebra. A polynomial of degree n has exactly n complex zeros when counting multiplicities. So in the first page, we added up all of the multiplicities of our real roots to get the degree. On the top half of this page, we added up all of the non-real roots to get the degree of our function, right? So just to recap, here we added up all the multiplicities of these are real roots, and they gave us the degree. Here we added our non-real roots, and it also gave us our degree. Sometimes you will have both in one function. One function can have a certain number of real roots, a certain number of non-real roots, and when you add them all up, that will equal your degree of that function, okay? The graph of the polynomial function f of x is shown in the figure above. It is known that x equals I times the square root of 3 is a 0 of f. If f has degree n, what is the least possible value of n? So remember, to get the degree, you're going to be adding up all of the multiplicities, and the multiplicities come from the zeros. So what I can do is find the zeros of the graph. So if I look on here, I see 2 zeros at -1 and +3. At x equals -1, I see that I am bouncing off the x-axis, so I know that has to be a multiplicity of 2. For x equals 3, it goes straight through and it doesn't do anything else, so I know it has to have multiplicity of 1. Okay? Over here, I know that this is an imaginary root, and I know that all imaginary roots come in pairs, so if I take the conjugate pair, I would get -I times the square root of 3. Okay, so let's see all of the zeros that we have so far. We have x equals -1 with a multiplicity of 2, x equals 3 with a multiplicity of 1, and then I have x equals I times the square root of 3 with a multiplicity of 1, and x equals -I times the square root of 3, also with the multiplicity of 1. So usually all imaginary roots are going to have a multiplicity of 1 unless they tell you otherwise. Okay, so if those are the zeros, then I can figure out what the degree would be because I would just add them all up. 2, 3, 4, 5. So the degree could be 5. Okay, so I'm going to write here, if f has degree n, the least possible value of n is 5, since there are at least 5 zeros. Okay, now the question was at least. Could there be more? Absolutely, there could be more. Okay, remember that for the ones that bounce off the x-axis, it's not restricted to a multiplicity of 2. It could be any even number. If this was multiplicity of 2,000, that would still be an even number and the graph would still bounce off the x-axis, right? And for the imaginary roots, they only gave us this conjugate pair, but who's to say there isn't another imaginary root that they didn't tell us about and we can't see it on the graph because they're imaginary. Okay, so when they ask you for the least possible number, do the smallest multiplicity. So the even multiplicity, smallest even is 2. The smallest odd would be 3. That would give you the least number. However, it could be way, way bigger because it could be any even number, even if it's a huge number. Okay, and then again, you can't see the imaginary roots. So all they gave us was that one. There could be more that we just don't know about. Okay, moving on to polynomial inequalities. So a reminder, when you write f of x, you are referring to the y values on the graph of f of x. When f of x is greater than 0, that means that the graph of f of x is above the x-axis. When f of x is less than 0, that means the graph of f of x is below the x-axis. Okay? If you ever forget what they're asking you about, you can just break it down. So for sure, you should know that f of x is y. So I can replace this f of x with y, and then when I'm like, what is greater than 0? Well, greater than 0 has to be the positive numbers, right? So I know that y is positive, and if I can make that connection, y is positive, oh, that happens above the x-axis. Same thing with the other one. When f of x is less than 0, the numbers that are less than 0 are negative. So then you can be like, oh, where y is negative, oh yeah, that's below the x-axis. So if you ever forget, just break it down to things that you know, okay? And then if you have difficulties figuring out the inequality signs of which one is greater than, which one is less than, what helps me is, when you put up both of your hands and then you hold them out like this to see which one, when you hold up your index and your thumb to figure out which one is your left hand or your right hand, and you know that your left hand makes the letter L. Well, I also use that hand because that same L looks like the less than symbol for less. Okay, so notice that this one here looks like the letter L. So that's how I personally remember. Some of you guys were taught the alligator thing, but I just like that because that less than symbol will always look like the letter L that is on my hand. Okay, so let's consider the function f of x above. Letter A says, where does f of x equal 0? Where f of x equals 0, that means they are asking me for my zeros, which if you remember are just your x-intercepts. Okay, so I'm going to look on here and I see that my x-intercepts are at -3, -1, and +3. So I'm going to write my solution. X equals, we said -3, -1, and +3. Okay, I'm going to box that in. We have 3 zeros. Where is f of x greater than 0? Okay, greater than 0, that means above the x-axis. Now, this does not have the or equals to at the bottom, so that means you are not going to include the zeros. Okay, so let me go over something over here really quick. Okay, so when you have the inequality sign that's greater than or less than, when you write your intervals, you're going to use parentheses. When you have the less than or equal to or greater than or equal to, you're going to use closed brackets. And you can remember that because you have this straight edge that kind of lines up with the straight edges on the brackets. And then just as a reminder, if you have positive infinity or negative infinity on your interval, you are always going to use parentheses. So even if everything else you're using closed brackets, if one of your intervals goes to positive or negative infinity, you need to put that infinity in parentheses. Okay? So where are we above the x-axis that does not include the zero? So above the x-axis, what I like to do is kind of shade it in. I feel like that kind of helps me. So above the x-axis, not including the zero. So that would be here to there, and also from here to there. Okay, so if I'm going to write this in interval notation, and remember this was just greater than, so I know I'm going to be using parentheses instead of brackets. We have -3 to -1 close parentheses union, and then 3 to positive infinity. And infinity always has parentheses. Okay, now you might be asking, well, you just said to not include the zeros. Why did you use the zeros? Well, the reason why, the point of using the parentheses is that these parentheses let the reader know you're starting right after that -3, but it's not included. If it had been closed brackets, that lets the reader know, okay, you're starting at the 0, which is -3. We can't say, oh, we're going to start at -2, because if you start here, you're missing this whole piece. You can't say -2.5 because you're missing this whole piece. You can't say -2.9 because you're still going to miss a chunk. We don't know the number right before -3. That number would be -2.99999999999, and that 9 would never stop. Okay, so you can't get an exact digit for the number right before -3 because there's an infinite number of 2.99999 right before that. So to alleviate that, you're just going to include the number of the zeros, but you're going to put them with parentheses, and that lets the reader know you are not including the zeros. Okay? The next one, f of x is less than or equal to 0. So for this one, you're going to be below the x-axis, and this one, you are going to include the zeros. Okay? So on this one, we are including the zeros. So what I'm going to do is start by I'm going to color code. So I am for sure including all of these numbers, and I'm including everything that is below the x-axis. So everything that's in green should end up in my answer. Okay, so there's no arrows here, but this is going to infinity. So from left to right, I start at negative infinity. And the negative infinity is not because I'm going down to negative infinity, it's because it's going all the way to the left towards negative infinity. So remember, your intervals are your x values only. So this, yes, is going down, but it's also slowly going all the way to the left. All the way to the left is negative infinity. Please do not confuse that. Like if this had instead been going down like this, all the way to the right is positive infinity. That's a mistake that some kids make. They see an arrow going down and they immediately say negative infinity, and that would be wrong. So you need to think about left to right, not up and down, okay? Left to right. So all the way to the left is negative infinity, and then I stop at negative 3. Now remember, we are including the 0, so I'm going to be using closed brackets, union, and then I have another closed bracket at the 0, negative 1, and then I stop at 3, close bracket. Okay, and that is the final solution. And then just as a reminder, again, even if everything else has brackets, infinity will always have parentheses, no matter what. You cannot put a closed bracket on infinity because we do not know the value of infinity. We don't know what the last number is. That's why we call it infinity. Okay. All right, moving on, solving nonlinear inequalities. This process is actually going to come up in a few other lessons, so it's important that you understand it now before we add on some more stuff to it. So the first thing, you're going to have inequalities. The inequality sign will either be less than or greater than 0, or it could be less than or equal to or greater than or equal to 0, or you can have a function that's greater than another function. So it could be a lot of different scenarios. Okay, what you're going to do is get everything to one side. So like if this was f of x is greater than g of x, what you would need to do is subtract g of x on both sides so that this cancels out and you get f minus g of x is greater than 0. So before you start, you need to make sure that on one side of the inequality you have 0. On example 4 and 5, we're good to go because these are already have 0 on the other side. But in case you don't, you need to subtract every single term to the whatever side you want to work on. Okay? And then after you have it equal to 0, you're going to change the inequality to actually just be 0, equal to 0. So I'm going to do x minus 3 times x plus 1 times x plus 4, and I'm going to set this equal to 0. This process is the same as what we did earlier, where you separate each factor, set them equal to 0, and then you can solve for the zeros. Okay, so we get x equals 3, x equals negative 1, and x equals negative 4. The next thing you're going to do is make a number line. Now don't make it too small because you are going to want to have enough space over here. Okay, now on your number line, we have negative infinity all the way to the left, positive infinity all the way to the right. So you're going to want to make sure that your numbers are, your zeros are from smallest to biggest. My smallest 0 was negative 4, then we have negative 1, and then we have positive 3. You don't need to put any other number on here that is not the zeros. And then also, let's say that we had repeated zeros. Like let's say from here we got negative 4, and then we also had a negative 4 here. You would not put negative 4 2 times. Just if you ever have a repeated 0, just write it one time on your number line. Okay. Now from here, I want you to look back at the question, because the question said, where are you greater than or equal, just greater than 0. So I know when I'm greater than 0, that means that my y values are positive. Okay, so what I'm going to do now is I'm going to use test values. So I'm going to pick numbers that are within the interval. to test into the linear factors we were given earlier. So before -4, I have -5. You could pick any number. You can pick -6, -7, -10, -1,000, whatever number that's before -4. Just make sure it doesn't come before -4. Okay? Between -4 and -1, I could pick -3. You could also pick -2. Between -1 and 3, I can pick 0, 1, or 2, but I would recommend if you can pick 0, that's the easiest one to plug in. So 0 is always recommended to use if you have it. And then after 3 would be 4, or you can use 5, 4, 5, 6, 7, 8, it doesn't matter. Okay, so what we're going to do is you see these factors here. I'm going to be plugging these into every single factor in here. So in the first one, I'm going to do -5 minus 3. Then I'm going to do -5 plus 1. Then I'm going to do -5 plus 4. Okay? Now from -5 minus 3, that equals -8. So I know that this is going to be a -8. -5 plus 1 is -4, and then -5 plus 4 is -1. You see how all of 3 of these are negative? What I'm going to do is annotate that by just writing 3 negatives down here. Now, when you multiply 3 negatives together, you are going to have a negative number, okay? You don't need to worry about the actual digit that you get when you subtract. Are you really asking yourself, is that number going to end up being positive or negative? And that's all that's important. Because what this negative is telling us is that this is below the x-axis. So all that this is saying that your y values are negative. Okay, that means you're below the x-axis. So let's keep going. Now we're going to plug in -3. So -3 minus 3 is negative. -3 plus 1 is negative. And -3 plus 4 would be positive. Okay, so remember we're plugging those into these factors here. So I'm plugging into these, each of those 3 x's, I just plugged in -3, right? -3 minus 3, -3 plus 1, -3 plus 4. And I got these signs here. Now I know that 2 negatives make a positive, and a positive times a positive is going to be a positive. Okay, now we're going to plug in 0. Okay, 0 minus 3, 0 plus 1, 0 plus 4. 0 minus 3 is negative, 0 plus 1 is positive, and 0 plus 4 is positive. A negative times a positive is a negative, and a negative times a positive is still a negative. A quick trick that you can do is just, if you have an odd number of negatives, like here we had 3 negatives, odd numbers are going to result in the number staying negative. Here we had 1 negative, and that's still an odd number, so that's why it still ended up being negative. If you have an even number of negatives, so here we had 2, that means that it's going to be positive. So a negative number, sorry, an odd number of negatives will stay negative, and an even number of negatives will be positive. Okay? All right, last one. 4 minus 3 is positive, 4 plus 1 is positive, and 4 plus 4 is positive, and 3 positives are going to be a positive. Okay? So let's see. We're looking for the intervals where we are positive. That was the original question. So I'm going to highlight the areas where we are positive, which are here to there. Okay, and then remember the question was y is greater than 0. That does not include the zeros. Okay, as a visual reminder, I would also recommend on your number line, when you have your zeros, put them as an open circle, and that'll just help remind you, like, okay, I am not including those zeros, so when I put my answer, I need to make sure I use parentheses instead of brackets. Okay, so I'm only going to include the intervals where we are positive. So parentheses, -4 to -1, close parentheses, union, and then 3 to positive infinity. Okay. So basically this process is the same as what we did at the top, except that at the top we had the graph. So when you have the graph, you can easily see what's above and what's below. You will not always be given a graph. And remember, on the AP test, for most of the questions, you do not have your graphing calculator. So when you're given a function and you have an inequality, you have to create this sign chart. This is basically saying, let's pretend this is the x-axis. Okay, this would be like something below, and then let's say it goes above, and then it goes below, and then it goes above again. So the graph could look potentially something like this. That's just telling you what's above and below without seeing the physical graph. Okay, let's try another one. Okay, so remember the first step again is to set the factors equal to 0 so you can find your zeros. So I'm going to separate these. X minus 5 equals 0. We're going to take the square root on both sides. These cancel out. You get x plus 2 equals 0. So x equals negative 2. And on this side, x equals positive 5. Okay, now if you're still stuck on the other part that this is multiplicity of 2, yes it is, but remember you are not going to write that 0 2 different times. You're only going to write it one time on your number line. So now we're going to create my number line. On the left I have negative infinity, and on the right I have positive infinity. From smallest to biggest, my zeros are negative 2 and positive 5. Okay, now my inequality symbol is less than or equal to, so that means that my y values are negative, right? And I'm also going to include the zeros. So when you're including your zeros, what I would recommend is putting a closed circle on them, and that will serve as a visual reminder that you are actually including the zeros. Let me make a note of that up here. So I want you to put, if it's less than or greater than, to put an open circle on the zeros, and if it's less than or equal to or greater than or equal to, put a closed circle on the zeros. Okay, and then that'll help remind you, am I going to use parentheses or am I going to use brackets? Because these rules that we wrote up here are still going to apply. If it's less than or greater than, parentheses. If it's less than or equal to, you're going to use brackets. Okay, so it's important that you know, are my zeros included or are they not included? So that'll just serve as a visual reminder to figure out what you are and are not including. And then I forgot to include these two blanks here. So while I'm up here, these two were positive or negative. So you're trying to figure out if you're getting positives or negatives on those intervals. Okay, back to this problem. Okay, so again, we're looking for the y values that are negative. We are including the zeros. So I shaded in where my zeros are. And I'm going to pick test values. Before negative 2, we have negative 3. In between negative 2 and 5, I can pick 0. And then after 5, I have 6. All right. Now, the factor here in the front is x plus 2 squared. What's nice about numbers that are squared is that they're always going to be positive, right? So if I had negative 8 squared, I'm still going to get a positive 64. If I have a positive 8 squared, I'm still going to get a positive 64. So what's nice about this factor being squared is that for sure I know that it's always going to be positive. So I don't really need to spend my time plugging things in like I did on the other one, because regardless of what I plug into it, if it ends up being positive, a positive squared is positive, and if it ends up being negative, a negative squared is still positive. So I know that my first factor is always going to be positive, okay? So I really only have to worry about plugging into the second factor. So if I put negative 3 minus 5, I know that's going to be negative. And a positive times a negative is a negative. Okay, remember the first factor was always positive, so you plug 0 into the second factor, which is 0 minus 5, that's negative, and a positive times a negative is a negative. Okay, the first factor is always positive, and then 6 minus 5 is positive, and two positives make a positive. Okay, for this question, we were asked for when the y values are negative or 0, so that would be from here to there, and from here to there. Okay, so those were the intervals where I was negative. Now notice that these intervals are side by side. If your intervals are next to each other, the only way that you can go straight through them is if your zeros are bubbled in. Okay, because my zeros are bubbled in, that means that they are included in my solution. I can go straight from negative infinity all the way to positive 5, and 5 is included, so I'm going to use a bracket. Okay, so this is the answer for this problem. Now, let's say, just as an example, that f of x was just greater. Let me put it over here. So I'm going to just put a side example. Let's say that f of x Instead of it being less than or equal to 0, let's say it was just less than 0, because that would change the answer. If it was less than 0, that means you will not be including this 0 in the middle, so you do have to stop there. So that solution would actually be negative infinity to negative 2 parentheses union, and then you would start again at negative 2 and go to 5 parentheses. Okay, so two completely different answers depending on if your inequality is just less than or equal to. So you need to be especially careful of what the question is. Again, if your intervals are side by side and you are including the zeros, you can go straight into the end like we did on this answer. If you are not including the zeros, you need to go from here to there, stop, and then start again and go to the second interval. So two completely different answers there, depending on the question. Okay. The next part of the notes is determining the degree of a polynomial given a table of values. If you're given a table of values with equal width input intervals, we can determine the degree of a polynomial by examining successive differences in the output values. The number of successive differences needed for the differences to be constant is equal to the degree n of the polynomial. Now, here's something that you might have overlooked. Your input intervals need to be of equal width. That means that your changes in x must be constant. Okay, so that's very important. So you need to make sure that you're checking your changes in x, and if they are constant, then you can proceed with this method to determine the degree. If they are not constant, you cannot use this method to determine the degree. So what we're going to do is figure out how do I get from one number to the next on both the left and the right. Okay, so for my changes in x over here, I have plus 2, plus 2, plus 2, plus 2. Okay, since my changes in x are constant, I'm good to go on the other side to start this process. Okay, so here we have negative 1, plus 2, plus 5, and plus 8. Notice that those numbers are not constant, so I'm going to repeat this process again. Okay, to get from negative 1 to 2, I add 3, 2 to 5 plus 3, and 5 plus 3 equals 8. So notice that the second time we did this, it ended up being constant. That means that this f of x has degree of 2. Okay, so f of x is degree 2 because the second differences are constant. Now we've done this process before where we find the differences, the changes in x and the changes in y. Remember that back then I had you guys circle this, and this was your average rate of change, and then this was your rate of change of your average rate of change. And if your rate of change of your average rate of change was constant, then that means that the table was quadratic. So this is another way of determining that the table is quadratic. Okay, so you just have to count the number of times that you subtracted. So this is the first differences, and these are your second differences, and the second differences were constant, so it's quadratic. Okay, so if your first difference is constant, it's linear. Second difference constant is quadratic. Third difference constant is cubic. Fourth difference constant would be quartic, and then etc. If it was 5 differences, then it's degree 5. 6 differences, then it's degree 6. Okay, let's do another one. First, make sure that your changes in x are constant. Here, I can see that they're all adding 3. And then on the other side, plus 2, plus 10, plus 17, and plus 23. They are not constant, so I'm going to do it again. To get from 2 to 8, I have to add 8, 10 to 17, add 7, and the last one add 6. They're still not constant, so I'm going to do it again. Now I see that it's just minus 1. So that means that g of x is degree 3 because the third differences are constant. Okay, and a polynomial with degree 3 would be called a cubic function. Okay, Okay. So again, the key part here is to make sure that these are constant, because let's say that this was 3, 5, 3, 3, then none of this would be true. It has to be equally spaced. Okay. Even and odd functions, so this is talking about symmetry on a graph. So for even functions, you are symmetric over the y-axis. So here's your y-axis, and you can see that if you were to fold this, these parts would overlap. So they are equally spaced away from the y-axis. So for even functions, I'm going to write that they are the same on the left and right of the y-axis. Okay, now it's important to note that y-axis part, because if I had, let's say, a quadratic like this, that technically is symmetric, but it is symmetric about x equals 2, not symmetric over the y-axis. So sometimes you will see things that are symmetric. You're like, oh yeah, they're the same on the left and the right, but is it happening over the y-axis? Because if it's not over the y-axis, then it is not an even function. Okay, so it has to be here that you're folding it on the y-axis and they're the same on the left and the right. Okay. For odd functions, you are symmetric about the origin. What that means is these graphs are going to look the same upside down as they do right side up. Okay, so yeah, I mean, they just look the same. In class, I had my kids hold their paper upside down to see it, but we're, digital, so you can't flip the screen around. But just believe me that it's the same upside down as it is right side up. Okay, all right. For even functions, you're always going to have opposite x values, but your y values are going to be the exact same. Okay, so when you're looking at a graph, I would recommend looking at where x equals -1 and +1. Okay, so at x equals -1, now this is not exact, but it's an approximation. We have -1 and +1. Okay, and when I look at x equals +1, I have +1 and -1. Okay, so if you look at these points, I have -1 for x, and then it switched to a +1. Okay, so for my x values, I have opposite signs. It's still the same digit, it's still 1, it's just that one is a +1 and the other is a -1. If you look at the y values, oh, this should have been a -1. -1, -1, sorry. So this is a -1, this was also a -1. So for your y values, you have the exact same sign. Okay, so the same digit, same sign, it is the exact same number. Okay. For odd, you're going to have opposite x values, and your y values will also be opposite. Okay, so again, if I look at -1, now this is just an approximation, let's say -1 and then +1.5. And then for x is +1, I have -1.5. Okay, so if I look at the x values, I went from a -1 to a +1. Okay, they're the same number 1, just that they are different signs. So my x values have opposite signs. And then for the y values, I went from a +1.5 to a -1.5. I still have the 1.5, it's just that now they are opposite signs. So the y value is also opposite. Okay. Now, if you were asked to do this by hand, what you would do is also plug in x equals -1 and +1. You can put any x values you want. You could put -2, +2, -3, +3. I just use -1 and 1 because it's easy to multiply those numbers out, so you're not doing extra brain work. All right, so I'm going to start by putting f of -1 into every single x. So all of these x's, I'm going to replace them with a -1. So we have -1 to the power of 4 minus 8 times -1 squared plus 1. Okay, -1 to the power of 4 is a positive number. If you have an even exponent, that negative will become positive, because what that means is that you have -1 times -1 times -1 times -1, right? These two negatives make a positive, these two negatives make a positive, so the whole thing ends up being a positive one, okay? Now PEMDAS says, let me actually write it. No, this is fine. PEMDAS says you need to do the exponents before you do multiplication. So ignore this -8 for now. You first need to do exponents. So -1 squared. Again, if you have an even number as your exponent, your negative will end up being positive. So this is now a +1. So now you have -8 times 1, which is -8. And then you still have a +1. 1 minus 8 plus 1 is equal to -6. Okay, now you're going to do the same thing, but now you're going to plug in a +1. So we have +1 to the power of 4 minus 8 times +1 squared plus 1. Okay, 1 to the power of 4 is 1. Remember, you're doing this part first. 1 squared is a +1, and -8 times 1 is -8, and then you got +1, which ends up being the same as what we had earlier, okay? So notice that on here, I see that I have the same exact y values when I plugged in opposite x values, because I plugged in a +1 and a -1. So for even functions, if you plug in an opposite x value, you're going to get the same y value in return, okay? Let's try g of x. So I'm going to plug in, again, -1 and +1. So we have -1 cubed minus 9 times -1. -1 cubed. Cubed is an odd number. So remember, an odd number of negatives will always be negative. So I know that -1 cubed will stay as a -1. And then those two, -9 times -1 is going to make a +9. And that's going to equal +8. Okay, now let's plug in +1. We got 1 cubed minus 9 times 1. 1 cubed is 1. -9 times 1 is -9. And 1 minus 9 is -8. So what you see here is that we got opposite y values when you plugged in opposite x values. Okay, the way I remember whether something is odd or even is that for odd, everything starts with O, right? We have odd, O, opposite x, opposite y. O, O, O. Okay, opposite x, opposite y, odd. Opposite, opposite, odd. O, O, O. And then, well, the other one is always going to be even. You only got two options, okay? So let's try some examples. Determine if the following polynomials are even, odd, or neither. So when you have a function, what you're going to do again is plug in +1 and -1. So we have 2 times -1 to the power of 4 minus -1 squared plus 5. Okay, so you got to do exponents first. So I'm going to bring down this 2. -1 to the power of 4. An even exponent will be a positive number. So I know this is going to be a +1. I'm going to bring down that negative because before I multiply by a negative, I need to square the -1. And a -1 squared is a +1. And then we got plus 5. Okay, so now you got 2 minus 1 plus 5, which is equal to 6. Now let's plug in +1. 2 times 1 to the power of 4 minus 1 squared plus 5. All right, we got 2. 1 to the power of 4 is 1 minus 1 squared, which is 1 plus 5. So 2 minus 1 plus 5, we got 6 again. Okay, so notice that our y values were both a +6. So that means if you have opposite x and same y, that means that you have an even function. Okay, let's try letter B. So we're going to start by plugging in -1 and +1. -1 cubed plus 3 times -1 minus 1. An odd exponent with a negative will stay negative. So -1 cubed is still -1. 3 times -1 would be -3 minus 1. Okay, -1 minus 3 is -4, and minus 1 would be -5. Okay, now let's plug in +1. We got 1 cubed, that's an ugly 3, sorry. 1 cubed plus 3 times 1 minus 1. 1 cubed is a positive 1. 3 times 1 is 3 minus 1. 1 plus 3 is 4. 4 minus 3 is 3. Sorry, I meant 4 minus 1 is 3. I was already looking at the answer. My bad. All right, so you see how we have a negative 5 and a 3? They are opposite signs, but they're not the same digit. Okay, that means that this is neither even or odd. Okay, if it had been negative 5, positive 5, then it would be odd. Or if it had been negative 3, positive 3, then it would be odd. If it had been negative 3 and then negative 3, it would be even. But anytime you have random numbers put together, it doesn't matter that the signs are opposite. If the numbers are not the same, it's going to be neither. Okay? Over here, when you're looking at the graph, go look for x equals 1 and negative 1. So negative 1 is up here. I have negative 1, positive 3. And at x equals 1, I have 1, negative 3. Okay? So notice that my x values were opposite. I had a positive 1 and a negative 1. So opposite x. And then if I look at the y's, I had a positive 3 and a negative 3. So that's the same digit, but it's an opposite sign. So my y values are opposite. Remember, opposite, opposite, odd. Okay, so that means this one is an odd function. Okay, last one. Look at x is 1 and negative 1. So at negative 1, my y value is positive 1. And down here at positive 1, my y value is negative 3. So my x values were opposite. I went from a positive 1 to a negative 1. But my y values went from a positive 1 to a negative 3. Okay, so notice that those are random. They are not the same number. 1 and negative 3 are not the same. So this is going to be neither even or odd. Okay, so we covered a lot today. If you guys have any questions, please leave them down in the comments below. Thank you so much for watching. I'll see you guys in the next lesson. Bye.